Hey everybody, and welcome back to Calc 3 Online. So this is just going to be sort of a chain rule part 2. The last one definitely going a little long, and I still want to talk about actually an important application of the chain rule. So this is really just a continuation of the last video. So I wanted to start off and just do another one of these kind of table problems because I think in the past, students have sort of struggled with them, and I want to make sure that you guys understand them well. So it says, suppose f is differentiable function of x and y, and you've got this g, u, comma, v, and then so, it's basically telling you here that u equals e to the u plus sine v, and this v function is e to the u plus cosine v. And then use the table of values to calculate the partial of g with respect to u at 0, 0, and the partial of g with respect to v at 0, 0. So let's start off with just writing down our chain rule. So g with respect to u is going to be f with respect to x, and then x with respect to u, and then f with respect to y, and then y with respect to u, right? And since f is a function of x and y, it's basically just saying that like x is that inner part e to the u plus sine v, and y is e to the u plus cosine v. Yeah. And then we might as well take our partials right now. So we know x with respect to u is just going to be e to the u, and we know we're going to need y with respect to u, which is just going to also be e to the u, which is nice. So based on this, this right here is a u, and this is a v based on that. So actually, I'm going to get rid of those things. So we know that if we evaluate this when u equals 0 and evaluate this when u equals 0, we just get a 1 and a 1, right? And so now we can do the partial, basically now we can plug in, I should say, here and here, right? We still need to deal with the partial of f with respect to x and the partial of f with respect to y. And that is where the table comes in, right? So we have over here, it's saying f with respect to x is, so we've got either 4 or 2, and then here we got 8 or 5. And it's not just something that you should just guess which one goes in there. You need to think about it a little bit. So we know u and v are 0, 0, right? So if we do f of e to the 0 plus sine of 0, comma, e to the 0 plus cosine of 0, right? Then e to the 0 is 1, sine of the 0 is 0, so this is 1. And then e to the 0 is 1, cosine of 0 is 1, so 1 plus 1 is 2. So basically that tells us what x and y are, right? X is 1 and y is 2 at this uv point here. So we really actually want this, right? We want f with respect to x at the 1, 2, so this right here. So now I can just go and plug this in there, plug this in there, and then we had the 1s, and then we can just go and add everything up. So this should actually be more clear. This is g of u at 0, comma 0. And then if you add all that up, you get 7. And I think for the sake of time, I'm not going to go through this, but you should do that too. It's very similar, except you basically have, a v here and a v here. So you'll be taking the other derivatives in here. And then you would just get something different because of that. I mean, it's just going to change some of this stuff right here. Okay. So another really important application of the chain rule is something called the implicit function theorem. So the implicit function theorem basically is going to give us a way to find the derivative of certain implicit defined functions. So if you have a function f of like x of t, y of t, the chain rule we developed for that was this one, right? We got this kind of diagonal pattern here. These were the ordinary derivatives because it just was one variable in there. So say you have some function that is basically an implicit function in y. So you have, I'm calling it capital F of x comma y is x comma f of x. Okay, so it's like a function of x, and all of that is set equal to 0. That's important part 2. That's set equals 0. Then we're literally just going to use this chain rule, okay? We have partial of f, this is kind of matched up with the z here, with respect to x is going to be the derivative of that first thing, which is literally just x with respect to x. So this part is just going to simplify to a 1. Then you're going to have partial of capital F with respect to y, and then y with respect to x, okay? And then, you're just taking the derivative of both sides, so you still get a 0 on the right side, right? So I'm going to write this just notationally a little bit kind of different, so I'm just for the simplicity. So f with respect to x plus f with respect to y times, this is not actually a partial, this is specifically a normal derivative, dy dx equals 0. And so the nice trick is basically if you rearrange this thing for dy dx, you actually have a little formula to find the derivative of implicit functions, so the ordinary derivative, notice. And it would just be the negative of f with respect to x over f with respect to y, if you just solve, this thing for dy dx. And if you did this for, you can extend this to like higher dimensions too. So, in higher dimensions, this part pops up still and you get a 1 there. And then the second term, something happens that's kind of different. So when you do y with respect to x, right, this part is going to be 0 because this function right in here, let me get rid of some of this y. This y was not implicit here. It was the z that was implicit. So there is no x component in this derivative right here. So that part goes to 0. Now the last one does not go to 0, right? This really would stay here. And then you can rewrite basically, I'll do it kind of over here. So now we've got f with respect to x plus f with respect to z, and then partial of z, partial of z with respect to x, okay? And remember, this whole term is gone, so that's why I'm putting a 0 there. And then again, it equals 0. And so then you can rewrite and do partial of z, partial of z with respect to x would equal negative f of x over f of with respect to z. So there's actually a little pattern here, and I'll show you how we use this here in a second. But basically what I want you to see is there's sort of a diagonal pattern, and there's always going to be a negative. And I could keep going. I could do the 4-dimensional. Well, this one is 4-dimensional, I guess. Sorry, this one is 3-dimensional. So I could do an implicitly defined 4-dimensional one, and you basically get 2 0 things in that one, right? Because you're going to have like x, y, z, and then your last variable is f of x, y, z. And so you'll get 2 zeroed terms in that one, and you'll always get a 1 in the front, and then you'll always be able to solve for this. But the pattern that I want you to see is that you basically have always a negative. There's always going to be a negative. And then there's like sort of this diagonal effect going on. So x's, y's, right? X's, y, or z's in this case. So it doesn't matter what you, whatever one you do, you're always going to get a negative, okay? And then this x is going to be, it's really capital F with respect to x. So it's like the full implicit function. And then you have this down here, f with respect to z. And likewise, this over here. And then this up here. And I want to show you how we can use this basically to help us do a lot of these implicit function derivatives a lot easier. So this was actually a problem that we did before, okay? And now it's actually super, super quick. So partial of z with respect to x is literally going to be the negative of f with respect to x over f with respect to z. And so we would have f with respect to x. We're just looking at this thing, and we just take the derivative with respect to x. So we're going to get 3x squared, and then the y term doesn't matter, z term doesn't matter, and so you get plus 6yz. And then the 1 on the other side is going to go away. I mean, you could even set the whole thing equal to 0 and just take the derivative, of both sides with respect to x and see that the 1 goes away. But that's like my f with respect to x. And then f with respect to z. First term doesn't matter. Second term doesn't matter. You're going to have 3z squared. And then you're going to have plus 6xy, right? And that is actually it. And really quickly, might as well do the other one here. Okay, so partial of z with respect to y, negative f with respect to y over f with respect to z. Always just those diagonals. So here you would get 3y squared plus 6xz. And then it'd be over 3z squared plus 6xy again. And just to show you, and that really is it, if you remember, this was a problem we actually did before. And before we did it, we just took the derivative of everything. And then when we got to the z, when we did the derivative with respect to x, we had to do product rule. We also had to do chain rule over here, right? We did all this work, okay? And we got this. Look at that, and then look at that, okay? They really are the same thing. I'll flip, and you can pause if you want. I distributed the negative in that one, but it really is the same thing. So it's a very, very, very handy shortcut. You definitely want to know this. And it honestly actually works for any implicit function. So you could teach a BC calculus student this trick to do implicit derivatives in BC calculus really quick. Because in BC, this is basically how you do it. But you could use the trick. All right, you're probably sick of chain rule, but I'm going to do one more very short problem. Because I think chain rule is actually something that's always a little bit tricky. So I want to make sure I give it some quality examples, basically. So this one is just kind of a neat application of implicit function theorem. So it says that you have function f of xyz equals 0 implicitly defines each of the three variables x, y, and z as functions of the other two. So z is function of x and y is x, z, and so on, right? So it's saying f is differentiable and all those partials are non-zero, which is going to be important because we're going to do some division because of the implicit function theorem. We want to show that thing right there is -1, right? And basically, you just go ahead and use the implicit function theorem. So partial of z with respect to x would be negative, right? F with respect to x, like capital F, over capital F with respect to z. And then partial of x with respect to y would be negative capital F of y over F with respect to x. And then the last one, again, just implicit function theorem. We're going to get F with respect to z up top, and then F with respect to y on the bottom. And then this is nice, because you can cancel this, you can cancel that, you can cancel this, and then you can cancel this and this. And since there's, 3 negatives going on, basically it all simplifies to -1. And that's it. So there's a lot of really important things here with the chain rule, and hopefully this is enough problems to start to feel kind of comfortable with it, because I do think it's one of these things that when students first see it in Calc 3, it can be kind of tricky.